You'll recall we began our discussion of parallel computing by the notions of parallel efficiency, so it's worth trying to figure out what is the parallel efficiency of MapReduce. Now let's assume that the data produced after the map phase is sigma times the original data size d. Further, we assume that there are p processors which in turn perform map and reduce operations depending on which phase they are used in, so we don't have any wastage of processors in this regard. Also, the algorithm itself is assumed to do WD useful work. W is not necessarily a constant. It could be, d squared or something like that. But the point is that there is some amount of useful work being done, even if you have a single processor, and that's WD. Now let's look at the overheads of doing the computation WD using MapReduce. After the map operation, we instead of D data items, we have sigma D data items in P pieces. So each mapper writes sigma D over P data to their local disk. So there's some overhead associated with writing this data. Next, this data has to be read by each reducer before it can begin reduce operations. So each reducer has to read sigma d over p squared, that is 1/pth of the data from a particular mapper. Since there are p different reducers, 1/pth of the data in a mapper goes to each reducer. And it has to read p of these from p different mappers, once again getting us the communication time that a reducer spends getting the data it requires from the different mappers as sigma d over p. So the total overhead, that is work that would not have to be done if we didn't have parallelism, that is writing data to disk and reading data from remote mappers, is 2d over p. Now if you look at the efficiency using this overhead, we get the WD is the time it takes on one processor, which is the useful work that needs to be done, and WD over P if we had P processors, but we have this extra overhead of 2 sigma D over P. We've added a constant C, which essentially measures how much time it takes to write one data item to disk or to read a data item remotely from a different mapper. Now we've assumed both of these to be the same constant. Simplifying this parallel efficiency, we get an expression which is surprisingly independent of P, dependent on W and sigma in an important way though. It's nice that it's independent of P because it indicates that the MapReduce process is scalable. You can get large efficiencies even with large numbers of processors. There is no dependency on the processors with the efficiency. However, it is dependent on sigma and W. In particular, as long as the amount of useful work that you do per data item grows, the efficiency ends up going close to 1, which is nice. On the other hand, if the extra data that you produce after the map phase grows, then efficiency can suffer and reduce considerably. So it's very important to use things like combiners to ensure that too much data doesn't get blown up after the map phase is done. In particular, if sigma ends up being dependent on p, then our statement here that efficiency is independent of p no longer holds. So be careful when computing this expression. Sigma is quite likely to be dependent on p, even though the expression hides that dependence. Now this is quite intuitive, and we'll compute the parallel efficiency of our word counting problem using this formula. First, I'll let you try that. Remember that when we were counting words, we had n documents, m total possible words, each occurring, say, f times per document on the average. So the total volume of data to be processed is n times m times f. Now, after the map phase, using combiners, we produce p into m partial counts, that is m different partial counts per mapper, and there are p mappers. At worst, there will be mp partial counts. Some mappers may not produce counts for words which don't occur there, but we don't worry about that. We assume that at worst there will be mp partial counts, which gives us sigma as the data after the map as compared to the data before it, and there you get p over nf. Now you see the ratio n over p creeping in through the sigma. So the fact that you actually had a shrinkage of data will end up helping us. Now let's see if we plug this in to our equation. We get the parallel efficiency is this expression, 2c sigma by w. Now assuming w and c are the same, which is a simplifying assumption in our case, we get an expression that looks like this. Notice here that as the ratio n over p goes very large, that means you have large volumes of data, large number of documents, then the efficiency goes to 1, as we would expect for a scalable parallel algorithm. So to summarize, we have seen that MapReduce is indeed scalable. In the previous case, we thought that our expression was independent of d and p, but we found that that creeps in because of the sigma. So the sigma is actually extremely important. The expansion or shrinkage factor after the map phase is critical for efficiency of MapReduce algorithms, and so we'll have to make sure that that is as small as possible if we want a scalable implementation. In particular, it should certainly not grow with the number of processors, otherwise we'll have a blow up in efficiency. So if sigma was growing with p, then you would end up having efficiency going down to 0 as large number of processors were used. It appears that this is indeed the case here, but notice that if you use large number of processors and keep the same problem size, you will get low efficiency. You'll have a lot of processors doing no work, which is what you expect. But if you used larger and larger document sets, then naturally you'd get better efficiencies, which is what a scalable algorithm is supposed to be.